you very much. So this is my last lecture to you, and unfortunately, I must leave immediately after the lecture. This is not unusual. When I give a lecture, quite often I have to leave the city. It happens. I have to travel to Arasatuba later today, and for a PhD defense at UNESP in Arasatuba. And after that, I can go home, I hope. Yesterday, I finished on this particular slide. The reason that I've used this, it's not to do with photosensitizers. These aren't photosensitizers. These are just conventional, I guess they're dyes. They're kind of a bright blue color. But these were used for, were proposed for treatment of tuberculosis in the 1950s. But the design of photosensitizers was kind of built on some of these compounds. And you can see that if you vary the length of the chain here, so methyl, ethyl, propyl, butyl, pentyl, you find that there is a kind of parabolic activity. Okay, so it rises to highest activity here and then down again. Same with the other side on here. So this parabolic relationship between activity and effectively lipophilicity or increased lipophilicity is quite a standard phenomenon in drug research, in medicinal chemistry. When you build a series of compounds and you vary their lipophilicity, you get that kind of change. If we look at photosensitizers developed from those kinds of compounds, most of the work was carried out by a chemist called Jim Foley at Harvard. Much better chemist than I am. But there's an interesting point here. What the operation was intended to do was to vary a group in here and also to vary the heteroatom in here. So you start up with oxygen. If you look at that, Nile blue itself, then lambda max 625, the quantum yield of singlet oxygen is very, very low. Okay, so effectively this is not a photosensitizer. It's not useful. So what Foley and his group did was to build photosensitizers, and they use what's called the heavy atom effect. So you add a heavy atom to the molecule, and you get interaction, what's called spin-orbit coupling. You produce more triplets, and therefore you can produce more reactive oxygen. So they varied the group here, bromine or iodine, and also they varied the atom here, either sulfur or later they went to selenium. So as you go further down a group in the periodic table, you find that the heavier the atom, the more of this spin-orbit coupling occurs and the greater chance of producing reactive oxygen species. Point here is that they increased the quantum yield by doing this. Okay, so if you compare, for example, Nile blue itself with the iodine version, so oxygen, hydrogen, oxygen, iodine, this one and this one, you'll see that the quantum yield here is about a fifth of the quantum yield here. So you can increase the amount of singlet oxygen using a heavy atom. But what also happens, and this is what I talked about yesterday, if you just design something on the basis of singlet oxygen, other things can happen to the molecule. So the log P value, so this is the kind of fractionation between water and oil that I showed you in the test tube in the first lecture. 0.25 positive goes to 2.55, so it's quite an increase in log P. So this is more lipophilic. Now if you increase lipophilicity, then you increase interaction with other lipophilic molecules, lipophilic biomolecules. So this relates quite a lot to what Mauricio Baptista was saying about the interaction of those compounds with the membrane, getting into the membrane, that kind of thing. Okay, now if you look at, so oxygen iodine here, and then we convert from oxygen to sulfur, okay, again, get a nice big increase, almost tenfold increase in singlet oxygen. That now is a fairly useful molecule in terms of its production of singlet oxygen. That will be okay to progress to further trials. But the log P now is 3.7, so a whole unit and some more of a kind of lipophilicity towards the highly lipophilic side of things. Problem with that then, once you get past about, I don't know, 2.5, 2.6, then you start to have problems dissolving in aqueous media. Okay? So although the singlet oxygen yield is increased, you've also increased the lipophilicity, perhaps a little too much. So if you think about the parabolic curve and activity, you're probably coming down the other side of the curve now. Okay? Now, just to make things very awkward, if we go from sulfur to selenium, we actually managed to drop the log P, and I've never understood that. I always intended to ask Jim Foley about that, and I never did. But that kind of spoils a nice relationship there. Science. As I said at the beginning and at various stages, I've always used methylene blue as the kind of main compound to build new compounds from. And as I said, it's quite easy to synthesize molecules which are better in terms of reactive oxygen species production than methylene blue itself. Quite easy. That also reflects in antimicrobial activity in vitro. Okay, so it's very rare for us to produce something, to synthesize something that's actually worse against bacteria than methylene blue. And you'll see that in some of the results that I'll show. A little bit of a kind of anatomy lesson, if you like. This is the chromophore, methylene blue, this tricyclic thing. And then we have two oxochromes, nitrogens here, which are electronically linked. So there's electrons here which can be fed in, and we can neutralize the positive charge here, form a positive charge there. So we can delocalize the positive charge across the molecule. It's not a point positive charge, it is delocalized. The other point is that if this isn't involved in pi bonding at the time, this can kind of rotate. So it's coplanar with the molecule if it's conjugated. When it's not conjugated, it can kind of fluctuate like that. There is a little bit of movement. And so the other point is the kind of typical structure. This is methylene blue and water. There's a small dimer aggregate kind of shoulder peak here, which isn't particularly useful. I'll talk about aggregation regarding another set of derivatives in a little while. But a nice intense red absorbing peak there, which is what we use to photoexcite methylene blue in cells or in the clinic. So, as I said, it's not the best photosensitizer. It's used because it's been used in patients, in humans, since 1890. And it's, as I said, very easy to make compounds which, at least in vitro, are better than methylene blue. So we can alter the chromophore, perhaps. It's quite difficult with methylene blue, but there are other ways. And most of the work, most groups have looked at changing the size, shape, substitution pattern of the oxochromes which attached to methylene blue. That's the kind of easy way to do it. Know just about everything about why methylene blue absorbs where it does, and we also know about the relationship between the oxochrome and the chromophore, the oxochromes and the chromophore here, and the substitution pattern. Okay, so we do this kind of mapping of electron clouds in the excited, the highest occupied molecular orbital and lowest unoccupied, that kind of relationship there. The transition of electrons between the two is the long wavelength absorption of these dyes, these photosensitizers. And it turns out that the more electron-releasing groups you have in here, and that would translate to, say, going from methyl to ethyl to propyl to butyl. These are bigger alkyl groups, so there's slightly more electron release into the chromophore. That actually raises the energy of the HOMO, and also raises the energy of the LUMO, but not as much. So the LUMO increases in energy less quickly than the HOMO, so in effect, the two tend to go towards each other. And that translates, of course, smaller energy gap, longer wavelength. It's quite a simple kind of story there. If we look at that idea, we did an awful lot of work on this series simple alkyls and all sorts of different derivatives when I worked with Stan Brown's group in Leeds in the UK. And as you can see, here's methylene blue here, lambda max 656 in methanol, and then as we go larger alkyl groups, more electron release, a longer wavelength for the reasons just discussed. If you go to selenium, again, there's a little bit of a spanner in the works there. The wavelength is slightly shorter, a great deal, but the important part in terms of putting selenium in there is to increase singlet oxygen yield, and it does that very admirably, very well indeed in all cases. So you get a big increase in singlet oxygen yield if you put a heavy atom in there. Again, that's a fairly straightforward relationship. When you get to the kind of pentyl and hexyl derivatives, though, again, very, very difficult to make anything like a nice concentrated solution for your testing. So they're not very water soluble. You need to go to perhaps adding a little DMSO or something to get them into solution. Again, if you look at the photoactivity, so Steve Gorman from the Leeds group published this in, 2005. I didn't realize it was that long ago. But again, you can see this kind of parabolic relationship. The photolicity increases, you get a maximum activity at the butyl stage. So that's whether it's the methylene blue derivative with the sulfur or with the selenium, maximum at the butyl. So all of those groups there would be carbon 4 units, butyl groups. And then once you get to higher substitution, it tends to fall off again. So that parabolic relationship, entirely due to the lipophilicity. It's nothing to do with singlet oxygen yield. As you see, the singlet oxygen yield here, more or less the same. It's not really much difference there. Okay? So if you wanted to argue about it, you could say, actually, the butyl derivative is slightly less singlet oxygen production. You've got higher activity in the biological test. So it's due to uptake and interaction rather than just the singlet oxygen. It works by singlet oxygen or other reactive oxygen species, as Mauricio was talking about, but it's really due to the chemical interaction, not it's not the ROS that are the kind of determinants for this. So that fits quite nicely with that parabolic activity idea. I mentioned toluidine blue. Toluidine blue is actually, in terms of the photoantimicrobials, toluidine blue is has a really important part to play. The kind of renaissance of photoantimicrobials began in probably the late 80s, early 90s. There's a guy called Mike Wilson who worked, he's retired now, at the Eastman Dental Institute, University College in London. And he published, I think, between 1989 and 1992, I think he published somewhere around about 30 papers, most of which used toluidine blue against bacteria, dentally relevant bacteria and fungi. So 30 papers is quite a lot in 3 years, even for someone who doesn't teach. So that was quite an eye-opener. It's around about the same time that I started to work on the antimicrobial rather than the anti-cancer, and he was quite an inspiration to those of us who started to work at the time. So toluidine blue is similar to methylene blue, as you can see, but instead of the dimethylamine group here, we have just a simple amine, so NH2, unsubstituted. And because of that, because it's only a small group, we can get other groups in here, or indeed in there. Methylene blue, you can't go in here or in here because these methyl groups get in the way. You can't actually further react that. So it occurred to me far more recently that we could vary, because the synthesis is quite straightforward, we could vary the group here, just put different simple groups in there and see what happens to the activity. One of the points with methylene blue, as I mentioned before, there's an aggregate shoulder, a small aggregate peak on a shoulder next to it, dimer peak. Toluidine blue, this is far more pronounced. Okay, so if you look at the UV vis, the visible end, you can see in toluidine blue they've got this huge big dimer peak aggregate stuff going on down here. Okay? The reason for that is these molecules are very, very flat, very planar molecules. So they will stack. If there's a concentration, they will stack on top of each other. One of the things I thought, we can vary the molecular shape. It gets sort of different activity if we put different groups in there. Sense? Well, perhaps we will. We don't know. We have to try and test it. But what we can do, we can put a large, bulky group there. So something which is not planar anymore. It's large. You can have large planar groups, but you can also have large groups which kind of are 3D. And so we went, I made methyl, ethyl, propyl, butyl, and then some benzyls and phenyl derivatives and all sorts of things. Turns out that if you look at something like the butyl, I'll concentrate on butyl because that was the one we chose in the end. Look at butyl, it's CME3 group in here where the methyl group is in toluidine blue. Look at the visible spec and you can see that the aggregate peak isn't actually a peak, the dimer peak, you've just got a kind of a weak shoulder here. Okay, that's fair enough, you can tell the difference. That also means it is able to produce singlet oxygen more efficiently because you've got a far higher kind of percentage of monomer. So the interaction with light is more efficient, so therefore you can argue that's why you produce more reactive oxygen, more singlet oxygen. We look at that in terms of space-filling models. Okay, you've got 3 toluidine blue derivatives here, stacked. Okay, they're not stacked directly one on top of each other. You've got one going that way, the one goes that way, the top one goes that way. That's the way that they would normally kind of stack together. Okay, so they take this much space. If we take that much space and then try and do the same thing with the butyl, you can see these butyl groups on the end. The molecules have to be further apart if you're going to put them together. And you can see how this is less aggregated or less easy to aggregate than toluidine blue. In terms of the performance against bacteria, this is a test. We used 3 hospital strains of Staph aureus and E. coli and Pseudomonas aeruginosa in terms of their gram nature. So you'll remember about this from the other lectures. Staph aureus is a gram positive. That's usually taken as quite easy to kill. And then we've got E. coli, which is usually more difficult, it's a gram negative. And then Pseudomonas aeruginosa, again, more difficult again, but it's still a gram negative. And because these are hospital strains, they can be a bit odd sometimes, so you get odd results. So we included in the test 2 conventional antibacterial agents. So this is trimethoprim, it's been around for ages, and this is levofloxacin, okay, which is a fluoroquinolone, which is usually quite active against gram negatives. We couldn't kill any of the hospital strains at all with trimethoprim. That's quite worrying because trimethoprim is still used quite a lot in hospitals. Levofloxacin was far better, but you see here this black tower, this is Pseudomonas. The activity there is quite a lot less than either E. coli or Staph aureus. So this is for the conventional antibiotics, antibacterial agents. Here's the kind of standard compound for all of this work. I always include methylene blue so that we've got some kind of idea where the activity should be. Here's toluidine blue. As you see, it's better against all 3 organisms than methylene blue. Not really a surprise. Then these codes, I apologize for these, I should have changed these. These were from when we had the spin-out company, we always had to code all the materials. This is the ethyl derivative. Toluidine blue is methyl. This is the ethyl. This is the propyl, and then butyl is in here. And the interesting thing about the butyl is that, I don't know why that arrow's moved there, it should be up here somewhere, but you can't actually see the column for the Pseudomonas. We've actually got kill against Pseudomonas, a hospital strain of Pseudomonas, at somewhere around 300 nanomolar. All the rest of these are in micromolar. So it's a really quite an interesting result, and it reflects both the increased uptake, the lack of aggregation, and the increased singlet oxygen. So all of that makes, I hope, a logical story, and we can see that it actually works. But of course, this is still in vitro. So what we are waiting for at the moment, we're working working with the group where I go today in Arasatuba. They are working in kind of animals, and we hope that once the animal tests are through, that we can get into human volunteers as well. So it's quite a long story, but it's quite a nice story for me. Just a note about drug resistance and conventional agents and the lack of new conventional agents. I don't know if you saw this. This is from a couple of years ago. In Science, there was a huge media splash from Scripps. They've made this new vancomycin derivative. I talked about vancomycin yesterday. It's actually not that spectacular in terms of its shape. There are various different new derivatives of vancomycin over the time, and none of them seems to have made it into the clinic. This new derivative here has bits of these other vancomycin derivatives attached. So it's a kind of hybrid of all sorts of different vancomycin derivatives which have been tried previously. It's not a new molecule. Okay, the only different bit is this bit here, which is a reduced amide. It's normally a CO bond there. Okay? So this new super antibiotic, that was how it was published. It's super antibiotic, I guess because you've got super bugs, so you have to have a super antibiotic to fight that. Incredibly expensive to make. So if you think about worldwide drug resistance, there's an awful lot of the world that isn't ever going to see any of this. The other part to notice about this is that there's a positive charge here in normal physiological media, so when you'd expect this kind of thing to be interacting with bacteria. There are the groups around, so that NH there, that NHME there, and also now this NH here. All of these will be positively charged. They'll be protonated. What you've actually got is a tetracationic derivative of vancomycin. It's never really talked about in the literature that kind of accompanied this stuff. So I'm fairly sure that that's got a kind of a role in the activity. So I'm only including that because there was such a huge media coverage of it. So all the news, it was in all sorts of scientific journals. But the thing is, this is a super antibiotic, according to this, but we know fine well that just using standard photosensitizers, we can destroy vancomycin-resistant enterococci quite easily. Vancomycin-resistant enterococci, VRE, is probably one of the biggest threats in terms of gram-positives in hospitals. Probably more of a threat these days than MRSA. But there's quite a lot of literature in terms of fairly simple photodynamic action against VRE. So that means then that something like methylene blue must also be a super antibiotic, doesn't it? The same reasoning. So there are various people involved in this. Where are we? Kitano is on this paper here, again with Martha from USB. But these are papers from the kind of 2000s, 2010, 2013. We actually published, a group in Preston published in JAC in 1999, the first publication on photobactericidal activity against VRE. So that's 20 years ago now. And still there's no interest in using methylene blue for that kind of treatment. It's far more easy, obviously, to go like to use a molecule like the Scripps one. It's cost an absolute fortune, and a lot of the world won't ever be able to use it. So talked yesterday and the day before about this molecule here, which we again now will call DO15, okay, officially, since I invented it. Originally it was called DO15, that was the series, and it was the 15th one. Again, this was from 30 years ago, 1989. It's sometimes called S137, but again, that's one of the company codes for the molecules that we used. Synthesis here is the same as the synthesis of the toluidine blue derivatives that we looked at. You've kind of got two halves of the molecule. You oxidize them together, and you end up with the methylene blue derivative. You can see the chromophore, oxochrome here, but also an extra ring, or an extra two two rings on there. So there's a huge amount of variation in terms of physicochemical properties available if you do this kind of approach. If you change a methyl group to an ethyl, you don't get a huge change. But if you have this kind of thing, you've got a lot more hydrocarbon in the end or both ends. And the amount of hydrocarbon here is what allows that interaction that Mauricio was talking about in the membrane. Okay? So these are, again, you'd expect these to be quite active in bacteria. So both the tetracyclic and the pentacyclic derivatives are all completely original molecules. You compare them to the lead compound, that's what the lead compound's there for. You get increased lambda max, you get increased log P, but it's manageable log P. It doesn't go crazy, it doesn't go up past 2, 2.5. It's okay, it's below 2 usually. And in terms of the biological tests, very much improved performance against bacteria and also against fungi. So that was a result. However, the singlet oxygen efficiency isn't great compared to, there's not a huge increase that you would expect as we've seen in other molecules. And that again turns out that's because we're not looking at reactive oxygen, singlet oxygen in cell kill. As Mauricio was saying, the type 1 route is important when you've got very close contact with membranes, for example. So that kind of explains why we've got higher photobactericidal activity, but perhaps not a similar increase in reactive oxygen species. Just to show you the increase in wavelength. Now, unfortunately, this red line here, the lambda max goes out to about 683 in water, so it's quite an increase compared to methylene blue. This one is actually slightly impure. This is an impurity in the system. I'd missed that. So we get an increase in wavelength compared to the lead compound. In terms of, again, photobactericidal activity, gram-positive, gram-negative, and a single strain. And we can see the activity much better than methylene blue. It's the DO15 one here. And we had, I think, about 50 or 60 different derivatives in this particular series, an awful lot of chemistry done there. It was an interesting project. So all of this synthesis and all of these molecules, we have to check them and test them and analyze them, see what makes them perform in the way that they do, and we can come up with all sorts of kind of relationships which do tend to work most of the time. Heavy atoming substitution, as we would expect, increases the singlet oxygen yield. What we can do with amino oxychromes, what we can do with extra rings, extra fused rings like the Nile blue derivatives, all of these things. All of this is quite well understood. So that means that we can predict the kind of molecular properties quite easily, but it's always fun to make the molecules and see if you're right, okay? Just nice to have time to do that in the lab occasionally. This is kind of a cynical slide, I guess. We've got methylene blue, toluidine blue as two leads here. Activity against Pseudomonas aeruginosa. That tends to be the kind of yardstick that we use as something which is, if something's very good against Pseudomonas, it tends to be good against most bacteria. Methylene blue and toluidine blue, you see the activity here against Pseudomonas. And then these are probably the best performing ones from 3 series. I think we've got 5 or 6 series altogether. 7.8 compared to 50, 0.39 compared to 50, 0.39 compared to 25. So the huge increase in activity against Pseudomonas. We did all of this work for these 3 series in the spin-out company from 2008 or thereabouts. 5 years trying to kind of hawk these things around the UK and Europe, trying to get people interested. There was absolutely no interest at all. One that wanted to kind of take these on and test them. So it was quite a difficult time. Okay. For the rest of the talk, I'm going to talk about applications of the photoantimicrobials. one of the ones that you will know, I should say, also there are clinical slides coming up. This is methylene blue treatment of gingival disease. So in other words, where there's a gap between the tooth and the gum. You have that normally because you haven't brushed properly or whatever. Bacteria will build up within there. You get biofilms. So what you can do is you can kind of squirt methylene blue into the gap. Okay, so it's squirt. There's no injection into tissue. The cannula here is used just to make sure it's directed into the right place. It doesn't actually go into the gum. That's usually left for, say, a minute or so, or as I said yesterday, very rapid bacterial uptake, and then illumination with whatever. This is with a laser in the same place, and laser light application probably for, I don't know, 2 minutes, if that. So it's very rapid kind of treatment. These slides are from the guys at Ondine Biomed in Vancouver, and the research labs are in Seattle, in Washington. Again, these are their slides as well. This is just to show you kind of why we need to do this, where there's a gap between the gum and the tooth, here in the tooth, and you can see a bacterial buildup kind of idea. So we can get methylene blue or another photosensitizer into here, and as I say, rapid uptake and then illumination to get rid of the bacteria. Some idea of results. Again, all of these are from Nick Labelle at Ondine. This is before and after. Okay, so this is a standard dental probe, and you can actually see the gap there, I hope. Okay, so this probe goes an enormous amount into the gum. This broad red band here, okay, in the before shot, is this band here in the after shot. So in other words, almost all of this here is the gum up here. So there's a big space in there. There's lots of space for bacteria to kind of grow. Okay, so roundabout, according to this, we generalized blood bleeding on probing, about 7 millimeter. We've got 3 millimeter depth and no bleeding probing, so it's quite a nice, successful kind of story there. We can also look at skin and nail infections. And don't forget, the photoantimicrobial approach is only going to be useful, at the moment at least, on localized infection. Localized doesn't necessarily mean to a very small volume. It just means that it's in one place. Okay, so it could be, as here, this is onychomycosis. It's a fungal infection of the nail. You may have seen that before. And you can treat this with methylene blue. These are slides from Jean-Paul Tardivo, who's in San Paulo. Treats with methylene blue and then illuminates with red light. And this is probably, I think it's one treatment a month, so it's probably 3 months. But again, treatment's very rapid. The alternative to that, you use conventional agents, is to take oral terbinafine, usually terbinafine, which is an antifungal agent. It has several different side effects. And apart from anything else, if you can get treatment locally that doesn't use an antimicrobial, then that's what you should do, I think. The more antimicrobials we use, the more resistance we're going to find. We find quite often terbinafine-resistant candida, for example, now. This is entirely due to the fact people are using too much terbinafine by mouth. There are other kind of sometimes psychological effects with terbinafine as well, which is kind of recorded. Okay. And this is another of kind of Tardivo's patients. This is a herpes lesion, herpes simplex lesion. And in this particular patient, this is a kind of a wet lesion. Didn't respond to standard antiviral treatment, the kind of acyclovir cream that you can get. You can normally use that for cold sores. It normally works quite well. This didn't respond to that, so in other words, it's resistant herpes simplex. Same approach. There's a close-up of this. Treatment with methylene blue. Okay. This is in November 2018. Sorry, November 2012. I don't know why that 18 is there. So between November and January, we go from this one treatment to this. This is nicely healed. It's not the same color as the rest of the skin, but it's healed. It's healthy skin. And so this is an example where you've got antiviral resistance. If you've got antiviral resistance with a herpes cold sore, then that is actually quite difficult to treat. It's wet and it's uncomfortable. So again, that's a very useful use. If we think about the whole approach, I mean, this slide here could have been absolutely enormous. I've just picked a few different bacteria which are relevant. So bacteria, gram-positive, gram-negative, molds and yeasts, so all different kinds of fungi. Envelope viruses, typically. I've got another slide on viruses later on. But also protozoa. We started a project between those in Liverpool and the guys in Ribeiro, looking at what most of the world, what the northern hemisphere call tropical diseases, which are kind of endemic in the kind of southern hemisphere and tropical regions. So we're looking at things like leishmania and trypanosoma, again, in vitro to start off with, but we would hope to kind of progress. In terms of what we might do, I think I've probably been preempted because I think we can do this, or you can do this already in Brazil. If you look at simple tonsillitis, simple bacterial tonsillitis, you can see exactly where infection is, where the kind of plaques of bacteria are. And very simple to have either a kind of a solution that you might gargle with, or perhaps some kind of lozenge that you could kind of just have in the mouth for a while, and that would very rapidly be taken up by these bacterial plaques. So once you've done that, you can just put the light source into the mouth, okay, and just kind of illuminate the back of the mouth and the throat there, and that would be enough to destroy the plaques, get rid of the bacteria. If you compare what we normally do, okay, and this is fair enough if it's a bacterial tonsillitis. Most tonsillitis cases, as I said the other day, usually around about 95% are viral, not bacterial. If it was a bacterial tonsillitis, you would usually have perhaps 5 or 7 days of an antibiotic, which you would take by mouth. So that means that the whole of the body gets a dose of an antibiotic before it comes back and hopefully clears up the tonsillitis. So the kind of direct approach, I think, is far better. And I did hear in a conference in London in December from someone who'd just come back from Brazil that they'd seen somewhere in Brazil, and I can't remember where. I'm guessing it's Sao Paulo somewhere, where this kind of methylene blue lozenge idea was used in exactly that particular way. So I hope that's the case, because it's a very good use of the technology. Oh, if we can do that, we can certainly do this. This is oral thrush. So here the kind of plaques here are fungal rather than bacteria. Exactly the same idea. We can treat with a cationic photosensitizer, illuminate, and destroy the bacteria. Oral thrush in youngsters, in babies, is quite often treated, even now, with crystal violet. So just take this purple stuff, you give it to the child. I have no idea how you do that. But there are pictures. If you look on Google, look, oral thrush and crystal violet, and you get this picture of this child, and he's got kind of he looks like he's been eating blackberry pie for about a week. He's got purple all around here and all in his mouth. So but that's just conventional treatment, crystal violet. If you use crystal violet and a light, it'd be a lot quicker. It is already out there. So this kind of approach, I think, is the way forward. If we go a bit further than that, you can get a local infection in the stomach with local colonization, I guess, in the stomach with Helicobacter pylori. And we know now that most gastric ulcers are caused by that. So we can And we can take a photosensitizer into the stomach. There are quite a few publications on this from a kind of theoretical point of view. And we know that we can knock out Helicobacter pylori with a number of different photosensitizers. So you could do that, and you could use a gastroscope to deliver the light. You could also use a gastroscope with an attachment to deliver the photosensitizer. So localized infection, that would clear up the Helicobacter. Now, having kind of being scoped into the stomach might not be everyone's idea of a kind of fun trip to the doctors. And I think normally the triple therapy which is available is normally enough to clear that up. So perhaps this is a step too far, I don't know. But, I would suggest that since the kind of standard biological stain for Helicobacter is actually toluidine blue, know that it's selective for Helicobacter. So again, that's the opportunity is there. Similarly, we could look at pulmonary treatment, same idea. Using an endoscope, we can introduce the photosensitizer into an infected lung presentation. And we can illuminate this way. Or if we use a long wavelength photosensitizer, perhaps we can illuminate from outside and through the chest wall. So there are a number of treatments. There's TB, of course, pneumonias, the kind of infections that you get, chronic infections with cystic fibrosis. Again, that would be a useful approach. And I mentioned yesterday, I think, PCP, pneumocystic pneumonia. I wanted to cover this because this is a group which I think Christina was involved in. It was published in 2017, which I saw at the time, and I was completely blown away by this. So this is pneumonia introduced into a mouse model. Okay, so strep pneumoniae introduced into a mouse to generate pneumonia, and then introduction of ICG, which is an infrared absorbing photosensitizer, indocyanine green. It's okay to use in patients. It's used in humans anyway for other purposes. And then illumination from outside. So there's no kind of internal illumination. It's illuminated from outside the animal. And the results were pretty spectacular. Okay, so for the PDT group with light, no bacteria recovered in 80% of the animals. Okay. No deaths in the PDT group. And in the control group, 60% mortality. That's an amazing paper. I think that's an amazing paper still. And that kind of shows what can be done, that kind of idea. So the only really internal procedure is the administration of the photosensitizer into the lung. The rest is all done from outside. So that's what we might do, but the Russians, surprisingly enough, have already done it. This is from around about the early mid-2000s. This is a patient here who has resistant TB. And I don't know if you can follow this, but there's a fiber optic here going from the kind of light source, just the kind of light end there, which is actually going into the right back, the lung. Okay, so they used chlorine E6. Okay, and this is the kind of sputum sample before. This is the control. This is the chlorine E6 sample. So the same. And then afterwards, after treatment, sputum sample, not many bacteria there at all, whereas there are more in the control. So I'm not sure how many patients. There were quite a few. I think it was tens of patients that they treated like this. Places that have problems usually after HIV has kind of reached the area. Quite often you get a follow-on epidemic of TB, and often it's resistant TB. So this kind of approach is kind of valuable. I'm trying to work out at the moment whether we can find out what's happened to these guys, because they've kind of disappeared. So I think this is really valuable work to demonstrate. TB obviously is slightly more serious than tonsillitis, right? This is, again, Tardivo's work. He's working on diabetic ulcers of the foot. Okay, so you've got this kind of zombie foot idea here. We've got big holes all over the place, and these are all infected. And he treats this with methylene blue, uses orange light, usually, around about 600, and you can see the kind of after effects of this. And he's treated quite a few hundreds of patients like this. These people, their only alternative, if they didn't have this treatment, would be to have their feet moved, amputation. Okay, so there are at least, I think, 400 patients in São Paulo who can walk because of this approach. I mean, sometimes their feet don't really look too much like feet, but they can still walk. It's very important. This is some work by Ondine. This is not infection. Okay, this is decolonization of patients who come into hospitals for elective surgery, usually. It's work done in the Vancouver General Hospital. That figure there, I think, is more like 30,000 now, because this is 2015. And the drop in post-op infections is down to around about 40% of what it was. So 60% drop in post-op infections due to this approach. And it's methylene blue applied to the nose, because this is where most of the, if you've got MRSA, that tends to be where it is. So you treat all of the patients coming in regardless for MRSA like this. And this is a kind of like a cotton burder Q-tip. Just put the methylene blue into the nostrils, and then illuminate with, just with light probes. Fairly straightforward procedure. And as I say, big drop in post-op. In terms of North America, that drop in kind of the number of patients infected actually is converted to massive financial savings for the hospital. So this is, again, important work. I talked to the NHS in the UK about this, and they just don't think they understood it. I'm not sure. But again, not really interested. It's not a difficult procedure. It's not going to hurt people. The inside of the nose will be blue for a little while, but that's, you know, a day or so. Otherwise, there's no kind of difference to the patient at all. It's not expensive. I don't know. Yeah, there's a question. I'm going to talk about viruses in a bit. How many deaths are there from influenza in a normal year? So normal means that there isn't a pandemic. The idea is be fairly quick. Okay, so between 400 and 600,000 deaths from flu in a normal year. Just to give you some kind of idea of scale. You remember in 2014 there was an Ebola outbreak in kind of West Africa, countries in West Africa. Press coverage went through the roof. There were all sorts of rules about who you would allow into the country. It's particularly bad in the States. But that whole epidemic, which covered 3 countries, there were only 12,000 deaths. In that year, I think it was 120,000 deaths flu. Difference. And if you think about flu, Spanish flu in the 1918-1990 global pandemic, between 30 and 40 million deaths. It's just in a very short period of time. That compares with the number of AIDS deaths that we've had so far since 1980. So always when you're thinking about infection, think about how many people are infected. And we know that our approach, our photoantimicrobial, will deal with flu, it will deal with HIV, and will deal with Ebola. Very easy. That I would recommend you start working with Ebola, but that's another matter. I want to finish on blood product decontamination. West Nile virus was virtually unknown in the US before that date, before 1999. HIV, of course, was not known anywhere. Nile virus is quite well known in North Africa, surprisingly enough. HIV wasn't known anywhere, wasn't understood until round about, or it was agreed on what HIV was by 1986. Both of these things are carried in the blood, and if you give blood, donate blood, then, and you have some of this in the bloodstream, then you can obviously transmit that into your donation. If we have an approach which protects against type of virus, not HIV, not Ebola, not West Nile, but a type of virus, so there are two types, there's either enveloped or non-enveloped, talked about that in the first lecture. If we can take out envelope viruses, an approach, then we're kind of protecting against all of these anyway, by default almost. There's a use, again, methylene blue, used for plasma contamination, or plasma protection, I guess you would say. You have a plasma bag, it goes through a loop into, it picks up a methylene blue kind of particles here, mixed in here and illuminated, and then passed through a filter to remove the methylene blue and into the final plasma storage bag. This technique is used in several countries in Europe and used in my country also. The point, I wonder if we can use that after Friday. Sorts of fun. The illumination of the plasma bag when it's got methylene blue in it, this thing is like a huge photocopier. Same kind of idea. So these are illuminated for about half an hour. That's sufficient time to destroy any kind of envelope viruses that are in there. If you look at the use of plasma, very, very useful properties. It can be fresh frozen plasma, cryoprecipitate, or kind of clotting factors, as well as albumin and globulins. So there's all sorts of useful things in plasma. So we do need to keep plasma protected. Okay. The difference between plasma, of course, plasma fraction, and red blood cells or platelets, those are the other two major fractions, is that platelets and red cells have cells in them. Plasma has no cells in it. So we can treat plasma quite easily with a photosensitizer. If we try and treat red cells, for example, with a photosensitizer, the red cells usually are too damaged. You wouldn't be able to re-infuse those. Quite often, if you use methylene blue, of course, they just blow up. That's not a good thing. So, emerging diseases. Does anyone know who these guys are, by the way? Things are called flying foxes. They're bats. Okay? And I include them there with the kind of usual mosquito because they are the reservoir for this stuff, which is Ebola virus. That's the natural reservoir, so I guess there'd be quite a few culls of flying foxes going on. They're actually the reservoir for quite a number of viruses, including emerging viruses. So, methylene blue plus light destroys envelope viruses. Now we use the word destroys because it does. It wrecks the membrane, it wrecks the capsid, and it wrecks the DNA, and it wrecks the enzymes and all the other engineering that goes with a virus. So if you look at HIV, you get damage to all of that, and you get damage to the reverse transcriptase enzyme, which is essential for propagation of the virus. But we can treat all of these different viruses purely on the basis that they are all envelope viruses. And none of those would stand up to treatment of methylene blue and light. So if that is in plasma, then it's gone after the illumination process. So these are established that you'll know about. There are some newer ones in here, things like Zika, you will know about in Brazil, obviously, chikungunya. Okay. These ones are very recent, but again, these are increasing. Hendra virus and Nipah virus. Okay, so the message is, if it's a microbe, we can destroy it with our photo-antimicrobial. I think that's it from me. Any questions? Be quick.
Questions?
Thanks. It's a really insightful lectures. I learned a lot. And you certainly turned me into a methylene blue believer. Yeah. Actually, it was very, very interesting about the Russian example. They did a chlorine E6 assuming that it's systematic delivery, not by the local photosynthesized delivery. And the combination of systematic delivery with the PDT for the treating of that, do you see there is a trend or there is any future in doing the systematic delivery combination of antimicrobial which will truly bring to the level of these super antibiotics?
I hope so. I don't really, all we can do is try. I mean, the more examples that there are, more chance there is that they'll be picked up by somebody else. There's a problem that Mauricio mentioned yesterday. The pharmaceutical companies don't like the idea of selling light. So that is a huge barrier. But yeah, I mean, the work in Russia, I'm trying to, talking to Valerie about it the other day. He has contacts there who still work on TB, so I'm going to dig in that way, see if I can find more evidence from that. So, but yeah, I think it's got huge potential. Yes, of course.
More questions? No? So let's thanks again, Professor Mark.